just work it by restarting. Yes, let's see. Both. Okay, so I just have a look at my screen. So as you read from lab 2 manual, this lab is to measure the diode characteristic. Okay, and just to choose, some famous diode, which is this guy 1N407G, and test the methodology, which is measuring the characteristic using two methods, just like what we did with Ohm's law. So basically, the characteristic that we want to measure is something that should be like this: ID, VD, and we have this exponential relation. Okay. So this is what we wanna, draw or plot. And what is the benefit of doing that? Basically, to know VBI. We knew from yesterday's lecture that when the diode operates means on. I mean, it conducts current. Usually the voltage, between 700 millivolt and 800 millivolt, okay, which is approximately equal to the built-in voltage or VBR. So that's the reason of measuring, or plotting the characteristic. Also, another two important characteristics is to measure I naught. Also, for that particular diode, it's very hard because it has very low I naught, which is a saturation current here in reverse. And one last, benefit of measuring the characteristic is to know the breakdown voltage. The one that I told you also yesterday at the end of the lecture. Okay. Rectifier diodes, and I will explain later in another lecture what is meaning by rectifier diodes, usually have very low I naught or saturation current, and also very high VBD or V is the breakdown voltage. So we will not be able to see the breakdown voltage of that guy here, okay, when we plot or the characteristics. So the objective is to measure the diode characteristics, okay, which is this plot here. And we're gonna do that using three methods, just like Ohm's law. The first one is using the step-by-step, which I'll call the step-by-step method. So step by step or point by point, whatever you call it, okay, in which simply we put a diode in a circuit, something like this. We have here a battery, a resistor, and our diode. We need a meter in series with a diode and a voltmeter. Or multimeter, whatever. And just to change the input voltage of the battery. So here is V input. And this is Mr. ID. And this is Mr. VD. And remember, of course, the relation is between ID and VD. So we want a VD to change, and it checks the ID value. But again, the diode is just like a resistor. It's independent. It's a dependent, element. It needs an external voltage, okay, to have a voltage drop and conduct the current and stuff, just like a resistor. So in order to change VD, we're gonna change the input voltage or the battery voltage itself. Okay. So for each value, for example, 1, 2, 3, whatever, okay, we're gonna check the VD value, the voltage drop across the diode, and we're gonna check the ID value, the current that goes through the diode. Okay, this is using the first technique here. Okay, so just to go ahead, I will share the other screen now. So here is the lab manual that I prepared. We have here, this is the battery, okay, and here is a resistor, and here is the diode, and I put 3 multimeters, one parallel to the diode, and I set it to measure the voltage, another one in series with the resistor, okay, and of course it is also with the diode to measure the current of the diode. And the third one here is just to check that I'm just, putting the right value for the battery, okay? So whenever I change the battery voltage, I just see the reflection of that change in this voltmeter or this multimeter that I set it to measure the voltage, okay? In that particular experiment, it changed when you conduct it, okay, when you change V1, it change it using these ranges here. So start first from -3 to 0, and by step 1, so -3, -2, -1, 0. Then from 0 until 3.2 volt, make the step 0.2. So 0, 0.2, 0.4 volt, 0.6 volt, 0.8 volt, 1 volt, 1.2, and so on until 3.2 volts. Then from 3.2 until 5, make the step 0.4, okay, and just to continue in that steps here, okay. Just one note here, 2 notes actually. So I want you, when you do this experiment, think about 2 things. First is the value of R1. Why we, I'm sorry, not the value of R1. Why we put R1? Why we didn't just, plug the diode in parallel with V1, okay? And why you can't do that? You can do that in Multisim, in a simulator, but you can't do that in a practical experiment, okay? When you have a real diode, real voltage source or power supply, you can just connect them in parallel and put whatever voltage you want, okay? I want you just to think about this, why we can't do that, or what will happen, okay, if you do this. And if you think about this, you will, appreciate the presence of a resistor like R1 here in this example. So I want you to think about this while you are doing the experiment. And another note that I want you also to think about is what exactly? Yeah, that's fine. So just think about this question, why we bought R1, okay? And just imagine what will happen if you just connect the V1 directly in parallel to to the diode, and I'm sure you will get the answer. If you didn't get the answer, I will, just after you finish, I will also, of course, explain about it. Okay, guys, you have 15 minutes. It's really very easy experiment. Okay. Also, because you will put very long series of values for V1. Okay, you might take time for this. So you have 15 minutes. Okay, prepare your Excel. Put the values there for each value you put for V input. Measure VD, the voltage of the diode. Measure ID, the current that goes through the diode, and using Excel just to plot them together. And let's discuss after 15 minutes what you get. Okay. Sweep, that's very fine. Okay, sweep the voltage, the input voltage, and get the values of the current ID and the values for the VD. Put them in the table and draw that plot here. Okay, and calculate the forward resistance for the last 3 points here. One note here before we go forward: this is 0.2 ohms. Very, very, very small resistance. Okay, so let's I'll just give a very quick hint about these results before we go to the second experiment. So if we go back to our one note here, okay, we discovered that the resistance here is 0.2 ohms. Okay. And here, the current was approximately 0, right? So let's start by this because this is easy. This is reverse bias, and the current is 0 between this point until this point before the breakdown. So there is a models for the diode that considers the diode open circuit. Okay, because the current is 0 when it's reverse. So if you know that you are working in that range here, the current is approximately 0, then you can consider the diode as open circuit. So for example, if you have a circuit like the one that we draw here, you can just remove the diode. It's a model. Yeah, it's still there, but the current is 0, so it's just like an open circuit. Okay, and if we go to the forward, we discover that the resistance is very small. It actually can be approximated to 0. So another model for the diode in that case, it's just like a short circuit or a forward resistance with 0. Okay, a short circuit and a battery was voltage 0.7. So you can replace this diode here with this, a short circuit, something like this, and a battery like this. But I will explain this later in the lecture, but just to give you a quick hint based on the results that we get. We get a very small resistance while in forward. We see that the voltage is doesn't change. We can say the change is very small in voltage, the forward voltage, which is around 0.7. Okay, so we can imagine the diode when it's operating in that region here as just a short circuit, series with short means it has no resistance. That's what's meant by short circuit. And a battery with voltage equal to 0.7. We can imagine the diode in that way. Okay, and in reverse, we can imagine it as an open circuit. You can just remove it from the circuit, and you will do that a lot in the future when we do circuit analysis using with diodes in these circuits. Okay, so let's go to the second experiment we have. So Danny, I was asking you about the value of the resistance. So I will just, after, just to refresh you guys and keep you active with me, I will just choose or pick randomly any person from you and ask him some question about, his progress in the experiment, because you should, you should finish this during the lab. Actually, it's very easy. So that's fine now. Okay, so let's go to the next screen and show you what we're gonna do with in the second experiment. So just like what we have done with the Ohm's law experiment. Yeah, this should be change diode characteristics. Just like what we did with Ohm's law, we're gonna do the same with a diode. Okay, so we're gonna draw the characteristic, automatically using the oscilloscope. Okay, and in that way, we'll do that exactly the same way as we did with the Ohm's law. So we're gonna connect the resistor with value of 1 ohm, okay, in series with our diode. And then, so this, again, this value here, which is 1 ohm, means that the voltage is equal to the current, because through the resistor, Ohm's law is, is achieved or, applied. So V equal to IR, R is equal to 1, so V is equal to I. And we know that oscilloscopes cannot draw current. They only can draw voltages. It's just like a voltmeter. Okay, but since the current is equal to the voltage across this resistor, so if we draw or plot the voltage across this resistor, okay, on oscilloscope, it will be just like the current. Good. Okay, for our experiment, for our application, we're gonna need to draw ID with VD. So we need an axis with VD, with voltage of the diode on it, and another axis with ID. So this is going to channel B or channel 2, okay, and this is the current. And this is the same current that passes through the resistor because it's, it's in series. All these are in series. The 100 ohms, the diode, the 1 ohm, and the source, all these guys are in series. So the current for them is equal for all of them. It's the same current. So we'll have the current based on that connection on channel B, and we will have the voltage of the diode on channel A. Then we can draw them together in what's called XY mode, just like what we have done with Ohm's law. Okay, but here, since we need the I, the current, on the vertical axis and the voltage on the horizontal axis, okay, we need to draw P/A, just like this connection here, P/A. So P/A means XY mode. Okay, so you have two signals input to the oscilloscope, and you're gonna draw them together, not versus time. Okay, so B/A means both the channel, both the signal on a channel B on the vertical axis, and in that case it's the current, because the current is equal to the voltage across R2, which is 1 ohm. And /A means both A on the horizontal axis, which is VD, right? So this will give you, the characteristic automatically. Just, very simple step, and you don't need to draw all, to conduct all these values by yourself. Yes, you can use a sweep in Multisim, but on a real world, you cannot use a sweep. There is no sweeps there. You will just change it yourself. And since it's non-linear relation, it's really, required to have a lot of points to draw it, or plot it precisely. Okay, to to have a good precision. So, but we can do that, you know, automatically using the oscilloscope. It's really, really very funny here. Just, you know, some very simple connection like this, and you will get automatically all the points that you have. You know. One thing here that really bothers me is that, you know, so you guys can see this very thick. I think this is a kind of, you know, because this is a model at the end, and the model of the diode is non-linear. So I think there is a kind of, you know, problem in solving, because behind the scene, Multisim is a software. So it's trying to solve non-linear equations together. So I think maybe, you know, each time it came up with different solution, because, you know, it makes a different techniques usually, you know, that solve nonlinear equations together, use some kind of random variables and stuff, something like this. So maybe this thick line here because of that, because we have many solutions, we can say, for VD and ID for the same input. So maybe you get many points. That's it. Okay, but we just gonna ignore that part and concentrate on the, you know, what we can say flat part. Okay, the one that we trust more, which is at the end of the relation in here. Okay, and in that bar we gonna consider it as a straight line, and, you know, take any 2 points. In that case here, this is 0.1, this is not, this is 0.2, and, you know, calculate the slope to know the forward resistance. Okay, so that's what we're gonna do with this. If anything here is not clear, just let me know, please. Now I can, you know, go deeper in this using the OneNote. Don't be shy again. If
it's kind of hard to read the range on the time base. Does that say 5 seconds on it?
The range, this one?
On the left side.
Yeah, 5 kiloseconds.
Kiloseconds, okay.
Yeah, you should look for this particular, you know, for this particular value here, the time base. Okay, you will notice that for small values, it's a kind of, you know,
yeah, it ended up being like a really thin line.
Yeah, it will be, you know, it will be fixed and good, you know, if you increase this value. That's my point. Okay, let's do it together. It's very, I have it already. So let's go and do it together. So I have here the automatic connections, okay. What I just need is just, you know, just a click right. Then double click here, and I have it. That's very nice. Just let me make it a little smaller. So if I decrease this, it will be not good. So that's good, that's fine. So it doesn't show. With other experiments, it was bad. I don't know why it doesn't do that here, but I found that it was more convenient and more stable drawing if I increase it, but looks like it was another experiment. That's fine. We are not actually, you know, interested in this. We are interested mainly here in these 2 scales, because we are not drawing with time. We are drawing 2 signals together. Okay. So let's see the 2 signals first. So I just YT. So these are the 2 signals. For example, this is the channel B now. This is the voltage across the resistor. Okay. And this is the channel A. This is the voltage across the diode. Wow. For some reason, it doesn't change with me. There is something wrong. Yes. Okay. Yes. Okay. So this is the channel B. I'm sorry. This is the voltage across the resistor. And by the way, guys, don't look sad or because we will learn in future lecture how to draw this, how to analyze a circuit with an AC source and diode and resistor, and get the plot of the resistor and the voltage across the resistor and the voltage across the diode analytically using a paper and a pen. Okay, so don't be scared from this drawing how that happens. Okay, so the input was just a sine wave. So the input is just a sine wave here, just a very normal sine wave. Okay, but the output, it's really scary. So don't be scared. We will teach you how to do that. How to do that by hand. Okay, not using oscilloscope or something. So this is the voltage across the resistor, and here is the channel A, which is the voltage across the diode. Let me draw it. Yes. Okay. We'll also learn how to do that. Okay, and why this clipping happen. This is very famous, application for the diode, which is clipping. But this is not our, our topic now. We are interested in BA, drawing B with A. So I will just, let that go to its, that's fine. Make it one. What was the voltage? Should we see that? 100 milli and 5 milli. This is 5 milli. And this should be DC with DC. Okay. So don't forget to set up the direct coupling here. Okay, DC and DC. So that's the diode characteristics automatically. Okay. So we are interested in this, in this piece here. If we set this to 1, okay, so each tick here is 0.2 volt, because this is 1 voltage per division. So 0.2, 0.4, 0.6, this is 0.8, and all the drawing is around 0.6 and 0.8, as we saw in the step-by-step measurement or point-by-point measurement. The voltage was around 0.7 volt, so that's correct, and it should be correct because this is the same diode. Okay, we didn't change the diode. Okay, so we will consider that this piece here from this point until this point is linear, and try to calculate its slope, okay, to determine the forward resistance of the diode. Okay, you guys have 10 minutes to do that. It's very easy. It will not take time from you, but please, respect the settings in here. Okay, the basic settings DC and DC, and this scales as well, and of course B slash A. Okay, you guys have 10 minutes. Just give me, after this to me, just post on the chat. Post on the chat the slope that you get, or the resistance, because the slope again here, the slope is 1 over the resistance, because I is on the vertical axis and V is in the horizontal axis, which the V is in horizontal axis. So the slope will be the the reciprocal of the resistance. Okay, so just post the resistance value. It should be very small. It will not be exactly equal to the one we just derive it from the step-by-step measurement. Okay, but because it's a different maybe range, because this is different range than the, it's hard here to set the exact range as the previous one, because we don't know where are these 3 points that we picked in the point by point measurement. Okay, but let's do that, okay, and get the new resistance for this new slope from this point until this point. Okay, guys, we have 10 minutes. Any problems, guys? Should I continue? So let's continue. Looks like everybody is okay and getting good results. So basically, you should get something, as I said, around 20.25 ohms. Okay, just some little tricks that you can use to measure. Okay, you can use, of course, these guys here. Okay, but if you are worried about them, or so for example here, this will measure the x, the b here. Okay, if you want to change it to the curve itself, just choose A. So this will be on 0.1 and this is 0.2. Yes, but it needs a little change. Yeah, yes. So you have here a point, just the tip of the curve, and here just the start. Okay, I told you measure from here to this point, which is okay. And don't forget, the scales. If you want to move the curve itself left or right or up and down, so for example, if you want to, move it left, let's say, left is horizontally, so we're going to play with the channel A because it's on the horizontal axis. So you're going to use this Y position. Okay, so now I'm increasing, so I'm going right. If I want to go left, I'm going to just do that. Okay. If you're going to go, let's bring it to its original position, which is 0. If you want to move up or down, you can do that from here as well. This will move it up. This will move it down. Okay. So that's just quick tips. And of course, you can use these, these bars, which are very, really convenient in measuring the slopes and anything. Okay, good. So that was measuring the diode characteristic automatically, okay, using that connection, which is not a practical connection. Remember, oscilloscope has just one common ground. So practical oscilloscopes, the ground of channel A and the ground of channel B should be connected inside internally. You can't see this, but you can measure, of course. You can put, for example, a multimeter on, this ohm in this beep mode, and it will, give you a beep because there is a short between them. So with that connection here, which was successfully shows us the characteristic because it's just a simulator. With that connection, R2 will be shorted. R2 will be shorted because here is the negative of A, which is the ground of channel A, and here is the ground of channel B, and both are connected internally in a practical oscilloscope, real oscilloscope. So there will be a short circuit on R2 here, the 1 ohm. So you will not measure anything. You will just see zeros. Okay. So let's now do the practical, implementation. We are trying to imitate as best as we can a real, implementation in a lab. So just as what we did with the diode, with the Ohm's law, we're gonna also have, a practical implementation or a practical, a practical connection for the oscilloscope. As you see, guys, here, I make one. So in our Ohm's law in practical implementation, this was 1 ohm. R2 was 1 ohm. Okay? And it was good because remember at that time, our interest here was 1 kilo ohm. The resistor that we want to measure the Ohm's law across it was 1 kilo, and 1 ohm to 1 kilo ohm is very small. Okay? So the voltage of a channel A, which is now from this point to this point. So what I have done here, I avoided this, you know, not practical or impractical connection, which will make R2 shorted in real implementation. And I just connected the two grounds to the same point, which is, you know, the ground point here. So the ground of channel A and the ground of channel B are both connected to the same ground. A channel B still is measuring the voltage across R2, but R2 changed it, and I will just tell you in a moment why we change R2. And now a channel A is measuring the voltage not across the diode alone. No, it's measuring actually the voltage across D3, the diode, and also R2, because it's measuring from this point to this point. So we need to make or to add, you know, a resistor which is R2 that has a negligible value if we compare it to the forward resistance of the diode. What was the value that we measured? We measured from the step by step around 0.25 ohms. We measured again the same value or approximately the same value from our previous oscilloscope connection, which is not practical, which is also 0.2 something ohms, 0.3 even. I know I am accepting such kind of big error, by the way, because, you know, it's not, you know, it's you know, there's something, it's not, you know, you don't know exactly where is the point that we measure between as in a step by step. So that's fine for me. Okay, but we have an estimate for the forward resistance, which is 0.2 something ohms. So I must put R2 here with very small value compared to that value. I put it here with 0.01 ohms, which if we compare it to 0.2 ohms, it's, you know, 20 times different, lower than this value. Okay, 20 or no, it's higher than this. It's actually, yeah, 20 times less than this value, which is okay. Okay, you can even choose, you know, 0.001, whatever, that's fine. Okay, so with that implementation here, okay, we're gonna measure the again the diode characteristics. So let's run it and see what we're gonna get. Okay, let's increase it more. And here it's the curve is just starting to climb up, so we just need to, you know, decrease. Yes, decrease the scale. So okay, and this is still 1 voltage per division, so we will not change this. And again, our curve here is between 0.8 and 0.6, just like what we got with step by step, and even the impractical connection of oscilloscope in our previous experiment number 2. Okay, so guys, do the same here, okay, with this setup. But again, look, you know, be careful with 2 things: the scales again, and now the vertical axis is not exactly the current. It will be the current if the resistance value of R2 is 1 ohm. but this is 0.010. So the vertical axis now is just the voltage across R2. So to convert it to a current, we must, divide this is the voltage. So divide it by the value of the resistance, which is 0.01. This will give you the current through R2. So look for this. Be careful with this. Okay. Again, R2 here is not 1 ohm. So the voltage on the vertical axis of P channel is not exactly the same as the current as we saw previously in experiment number 2 or in Ohm's law experiments. No, it is just the voltage across R2. And to convert the voltage to current, we must divide by the resistance value. Voltage over resistor equal to current of R2 here. And the resistor is 0.01 ohm. So be careful with this observation and try to redo the same stuff we did in the previous experiment number 2. And whenever you get a number, just publish it on the chat. And before we go forward, if this is not clear, or anybody needs a question, please don't be shy and ask me. So go ahead, you have 10 minutes, guys. Okay, you have 10 minutes. Whenever you get something, just publish on the chat. Okay, one last thing before we finish this, okay? So let's get back to the question why I bought the 100 ohms in series with the diode, okay? Anybody has a vision why? Or any answer for this question? Why I put this resistance here or not? No imagination?
It
Yes,
linearizes the current.
No. So let's ask the question another way. What will happen? I'm sorry, not this circuit, because we have still this resistance here. So let's stop that and go back, in here. So what will happen if I remove this 100 ohm? Of course, remove means I just connect this point here of V1 of the source with directly to the diode.
Well, it's going to draw a large amount of current.
Yeah, that's
very
right.
large.
Yes. It will be very, very, very large current. Okay. And the reason is that here I am forcing. So if I put this resistance, magically the diode will just take around 0.7 volts, and the rest of because of course voltage Kirchhoff voltage law. If I put 5 here, for example, this guy is very humble guy. We just take 0.7, okay, and the rest will be going to R1, 4.3 volts. If I put 10 again, this guy, you see the curve. It's always around 0.7. So let's say it will take 0.7 again, okay, and the rest, which is 9.3, will go to the R1 with 100 ohm. Okay, but if I remove this R1 and I just connect V1 directly to the diode, okay, let's do it, and make some small calculations. So let me share the other screen. This is the last thing we do today. Okay, so you see, guys, my OneNote, right? Can you see my OneNote or not?
Yes, we see it.
Good. So if I remove R1, it will be, a diode like this, and just in parallel our source in here. Okay. So basically, if I put any voltage here by voltage Kirchhoff voltage law, the same will appear on the diode. So if I put 30, for example, 30 will appear here. If I put 1 will appear, and so on and so forth. Okay. So let's measure the current. We know the I equal to I naught e to the power Vd over Vt minus 1. Okay. So let's, for example, put Vd equal to 1 volt, just 1 volt. Okay. So let's calculate this using, I'm just interested in this term, the exponential term. Okay. So let's do it using the software. Where is that guy? Just a calculator. Online yes. Let's see. So let's do it. You see, guys, my calculator now. Okay. So this exponential 1 over 0.026. What is the value we see? It's 5 point something to the power 10 to the power minus to the power 10 to the power 16. Okay, so it's very large. Just 1 volt. 1 volt. I'm not talking about 1 volt. Okay, so let's now change it to 30 volt, which was our final value. It's infinity, undefined, right? So that's the problem. So magically, okay, when you put a resistor in series with a diode, the diode is just an humble guy who just take his 0.7 volts, and the rest will go to the resistance in series with that guy. But even with that, it's not, of course it's not that simple. Okay, and even if you put a resistance, if it's a small value, you still have the the risk of having very large current, and you may destroy all your circuit, not just the diode, by the way. Okay, so that's why I bought the resistance, or usually bought a resistance in series with the diode. Okay, to prevent such large currents inside the diode, and hence, of course, the diode will break or anything else will break. Okay, so that's why I bought the resistance. So guys, you have again 1 week to finish the report. Okay, again, take screenshots, mark the points that you measure the current, the voltage and the current from, and the slope in each experiment, the first slope, whatever its value, the second, and just calculate the error. We will consider the value that we get from the step by step as our base or our reference. Okay, and we calculate the error from the other one based on our reference, which is a step by step. Okay, and you have 2 weeks. So 1 week it will be considered just full mark. In the other week, if you submit, it will be late. You can still submit. After 2 weeks, you can't submit anymore. Okay. So henceforth, in any homework we take, it will have 2 weeks of a window of submission, but it will consider be late after 1 week. So you have, guys, after this lab, 1 hour as office hours. So if you have any question or something, just let me know. Okay. And if you have something in the lectures, in the lab, also just let me know, that's fine. Okay. If you have even a general question about the homework, the submission, you can also ask. Okay. Otherwise, you just can leave the meeting. That's very fine.
See you tomorrow.
The what? Yeah, okay. See you. Bye. So any question, guy, if you have a question, just ask me. If you don't have, you can just leave.
Excuse me, Professor?
Yes, Muhammad, yes.
Yes. During the lab, my multisim kept crashing a lot, so I wasn't able to calculate the slope. So I was wondering, could you show how to calculate the slope using the oscilloscope?
Can you repeat the question? What's the problem that you have?
Oh, during lab, my multisim kept crashing. So I wasn't able to learn how you calculated the slope using the oscilloscope.
Okay. So you can see the screen, right?
Yeah, I see it.
So let's do it with, you know, the ugly one,
Okay.
this circuit. Okay. So I just here increase the scale of the horizontal. So whenever we take 2 points to measure between, it will be clear for us the voltage per division, the division, how many divisions we took. Okay. So for example, we are interested in 2 points.
Mhm.
That point in here is a cross section between this, you know, dashed white line and our curve. So this point here,
Uh-huh.
how many divisions? These are 4 divisions, right? And this point, the tip of the curve,
Mhm.
this is, it's not that clear. So we're gonna, you know, move the curve down so we can know precisely how many divisions we have.
Okay.
It's around 4 point, let's say 4.19, because this tick here is 0.2.
Okay.
Okay,
Got it.
so this may be 0.19 just
Okay.
before. Okay, so you have 4 and you have 4.19, just subtract them, you know, the delta x, we can say. Okay,
Okay.
now we want to know the delta y. So let's bring this back to its original position, 0 and 0. And here is the 2 points, this point in here and this point. Okay,
Mhm.
so if we move this, you know, no, that way. Okay, remember, this guy is parallel to this. Okay, so the same intersection here. So this is the intersection. How many divisions we have? We have 1.3.
Mhm.
So 1.3 divisions.
Okay.
Okay. And how many divisions for this one? This is clear. It's around, you know, maybe in the middle. So it's 2.9 divisions. So delta y is 2.9 minus 1.6.
Okay.
So you have delta x and you have delta y.
Right.
Now, take delta x and multiply it by the channels that represent the horizontal axis, which is this one, channel A,
Okay.
the horizontal. So multiply delta x by this value, 200 milli.
Okay.
Then multiply the delta y by the voltage per division of the y channel, which is B. Okay?
Mhm.
The 1 millivolt per division. And don't forget to divide the value that you get right now, delta y multiplied by the voltage per division of y channel or B channel, divided by 0.01 to get the current.
Okay.
Okay, now you have current and the voltage. You can divide voltage by the current, you get just
The resistance.
the resistance, right? Yes.
Okay. Thank you. Oh, I believe someone asked you a question in the chat.
Oh, I didn't see that. Can you explain 3C whether we can keep it to, okay, I can explain this, of course. So, okay, so let's do it with, You guys can see my OneNote, right?
Yes.
Okay. So who is asking this question? Just Arsenio. Okay. Okay. So we have here our diode. Okay. And here is the resistance that we bought. And just forget about any other resistance. Let's assume this is our, connection right now. Okay. So I'm saying that in order to draw VD with ID on the I'm sorry, the opposite. ID with VD. ID, VD. In the oscilloscope, we need two signals. One signal represents VD, another signal represents ID. Okay? Where are these two signals? First, oscilloscopes cannot measure currents. They only measure voltages. Okay? So we need a resistance that that has the same current as the diode. So we will put this resistance in series with the diode. Okay? And we're gonna draw on the oscilloscope its voltage, and this voltage will represent the current. If you want to make it exactly representing the current, we should make the resistance with 1 ohm, because basically V equal to, so this call this VR, so VR is equal to 1 ohm multiplied by IR, and the IR is exactly equal to ID because they are in series, so this is equal to ID. Okay, good. So in principle, if we have this imaginary oscilloscope that I didn't see before, that has two grounds, okay, and this is the channel A, will be connected to the voltage of the diode, and the channel B will be connected to the resistor. Now the signal on channel B is exactly equal to ID. So of course VR, the voltage of R, but in that case with resistance equal to 1 ohm, it's equal to ID. Okay? Good. Now the oscilloscope will do the magic for us and draw something like this. I explained last time how oscilloscope will behave in XY mode. It just take one point at the same time from the two signals and draw them together. One signal will represent the x-axis and another signal will represent the y-axis. That's good. Unfortunately, we don't have an oscilloscope, as far as I know, that has a common that has two grounds. No, oscilloscopes has common ground. So this ground in here and this ground are connected internally. If we test them using a multimeter, it will beep because there is a short circuit. They are the same point. They are connected. So this is not valid. This is not valid connection. So how are we gonna do it? Okay, that's fine. Basically, we must, make the two grounds connected at the same point. So the ground of A will be connected to the same ground as B. And the post of A is still connected to this point. Okay? And B will still also connected to this point of the resistance. Okay? The problem is we wanted in the first place VA, which is the voltage on channel A, to represent VD. I'm saying VA ideally should be equal to exactly VD. And VB ideally should be exactly equal to ID because the resistance is 1. That's okay for R because its resistance is 1. But that's not okay for VA. Because VA now, if we make, VA is measuring the voltage between that point and that point. So VA is actually equal to, currently, VD and VR, which is not right. Okay? So to get around this, we need VR, or we need VD to be much larger than VR, so that VA will approximately equal to VR. VD, sorry, VD. Okay, so that's what we want to do. Now the question is, how to make VR negligible to VD? We do that by making or by looking at the resistance of both devices. Okay, we have two devices now. We have our resistance. We will consider this a device for now, just between us. And we have our original device, which is a diode. Okay, so if we know the resistance of the diode, okay, we can choose R to be much smaller than this resistance of the diode, so that its voltage will be negligible, comparable to the voltage of the diode. Okay, and how we do that? We already have some idea from our first and second experiment that the resistance of the diode, which we call it forward resistance, is approximately around 0.2 ohms, 0.25 ohms, right? And now, if we keep R equal to 1 ohm, it's 4 times larger than the resistance of the diode. So it will have a considerable voltage drop compared to the voltage drop of the diode. So how to get rid of that? We make R we must choose R much smaller than 0.25 ohms. So it will have a negligible voltage drop compared to the voltage drop of the diode. Okay. So I choose. So let's now change this. So this is wrong, and we should change it to something very much smaller than 0.25. For example, 0.01 ohms. Now this will hold. Okay. And now we have another problem. Now the voltage on a channel B is not exactly equal to ID, but this is easy to fix, because simply now the voltage on B is equal to VR equal to 0.01 multiplied by ID. So this is what we will get on the screen. So any value you get from there, just divide it by 0.01, you will get ID. So that's easy. But the serious one was this problem here, that A should measure the voltage from the diode point here until.
I'm having trouble finding the voltage value for 3.
Oh, he speaks finally. What is the problem that you have?
For part 3, I'm having trouble finding the voltage value from the oscilloscope.
Okay. So let me repeat that again. That's fine. So this is basically as you see my screen, right? The oscilloscope screen, right?
Yeah.
Good. So this is actually the original. This is the original, plot that I have.
Okay.
Okay. This is for experiment number 3. So basically, we need 2 points on the straight line, and we can, just have delta x for these 2 points and delta y, and that's it. We can get the resistance. Okay. Okay. So let's choose 2 points. For example, this point in here is the tip of the curve, and the intersection. This is the second point. You are free to choose any point, but this is easy, which is the point of intersection between this straight vertical dashed white line and our curve, which is approximately a straight line in that area. Okay.
Is it okay to use a cursor like we did for the previous one? Like those two, the yellow line and the blue line?
Yeah, you can use, but for myself, I sometimes get confused with them, but let's do that. This is number 2. So what is the difference in here? The difference is this is 0.2 voltage per division. Around 0.2. Okay. 0.9 something. 0.19 voltage per division. If we multiply 0.19 voltage per division by 200,
So why can't we use find slope? Or why wouldn't that work?
where is that?
Where if we did y2 minus y1 to get the slope.
Yeah, so you have, this is what I'm saying. These 2 markers are usually, they confuse me, especially in XY mode. Okay. So I'm not using them. But anyways, you have, here 0.19 divisions. Okay. So you should multiply this by 200 millivolts. And for the vertical, now it's really not so convenient to measure the vertical delta from here. So we're gonna move the curve to the left until it intersects with that guy. Okay. So how can I move that? I'm gonna move it horizontally. Left or right means horizontal, up and down means vertical. What is the signal that is in horizontal? It's A. So I should play with this, position markers. Good. So that's exactly its original position that was here. Okay. And here is the point you are interested in, which is the intersection of the curve with the white, and it's actually at 1.6 division. Okay. And the second one, this is clear. It's around 2.9 divisions. So you have these 2 divisions, subtract them from each other, then multiply them by 1 millivolt. Then divide by 0.01 ohms to get the current. Now you have the actual current difference and you have the actual voltage difference. You just divide the voltage difference by the current difference. You will get the slope, or not the slope, 1 over the slope, which is the resistance. Is that clear?
The problem I'm having is I'm used to using the cursor, so I do y2 minus y1 over x2 minus x1, and I get.
You mean by the cursors these two markers or what?
Yeah.
So don't use them. Just make it with. I know how to use them in YT mode, this mode, which is the normal mode, the conventional mode of the oscilloscope. But I don't know exactly how to use them in the XY mode, because the value that was written here, I don't know if it's the value before multiplying by the voltage per division or after multiplying by my voltage per division. Okay, so it really confuses me a lot. So I'm not using them.
Oh, it's because I think they're after, because my x value was like 840, and if you're to do like 4.2 multiplied by the scale, it gives you around the same value.
Good, good. Thank you very much.
But the problem I get is when I do that way, and then I divide, I get a slope of 0.0309, and then I don't know what to do after that. If I divide that by 0.01, because if I do, it doesn't give me. It gives me like a resistor of 3.
So you get the delta y, right? How much is the difference in the slope of delta y? I'm sorry. How much is the y difference between, for example, these 2 points?
My y2 and y1. Is that what you're talking about?
Yes, yes.
My y2 is 2.816 and my y1 is 1.059. So the difference.
This is the voltage per division. I'm sorry. This is the number of divisions, or what exactly? So give me the difference in the divisions.
Okay.
Or the divisions of this point and the divisions of this point. Okay. Then I will subtract it myself and multiply by the voltage per division that you will give me also.
I'm not using that. Is it like about 1.2 divisions?
This is Y2.
Oh no, y2 I got 2.816 minus 1.612, and I get 1.204.
1.204. This is the voltage, but this is the divisions, right?
I think it's already multiplied with the channel.
No, I said to you, I'm not sure about how the markers are doing in YT mode. I'm sorry.
Yeah, I think the markers already have the channels multiplied into them.
So if you did it in the easy way, maybe it's longer, but it's easier. Okay. This confusing way, you will get something like, again, 0.3 or something.
Okay, so can you show me the other way then?
This is what I was explaining to you. So you see which screen you are seeing right now?
Yeah.
The tab, yeah, you see the. So basically, you choose 2 points in X and 2 points in the same 2 points, okay, and subtract Y of the first point minus Y of the second point, X of the first point minus X of the second point. Okay, so our original curve was like this. This was the original position. We
Yeah.
chooses 2 points. This point at the tip and this point, which is the intersection of that white vertical line with the curve. Okay. Then, what is the x of the first? What is the the number of divisions of the first points?
Like 4.2.
Yeah, this one here. So the second point has easy number of divisions, just 4, because it's an intersection, right?
Yeah.
So 4 divisions. That's good. So we have. Let me do it with you. So we have 4 divisions minus. And what is the number of divisions of that one? It's not clear. So let's bring it down from channel B, because the channel B is on the vertical axis. So we change the position of the curve using channel B Y position. We bring it down. Yeah. So looks like the tip intersects with our horizontal axis here at that point, which is around 4 divisions 0.19. So 4.19. Okay. So the first point has 4 divisions. The second point has 4 divisions 0.19. Because this tick here, this first white tick is 0.2. So this is just before this, so it can be said 0.19. So we know now the voltage per division for the the delta x, but as divisions. To convert this into voltages, okay, we must multiply by the voltage per division of channel A, which is the signal on the horizontal axis, which is 200 millivolt per division. So I should multiply 4.19 minus 4 multiplied by this subtraction should be multiplied by 200 millivolt. Okay, this will give me delta x in voltage. Now I convert everything. Now
So
let's do the same. Yeah, continue.
So it's what, 38 millivolts?
So let me do it with you again. So this is 0.19 multiplied by 200. So 19 multiplied by 2, it's a 38 millivolt. That's right.
Okay.
Okay. So now let's do the that guy for. Let's move it to its original position, and let's try to get the delta y now. So again, these are our 2 points. It's not clear from here. So let's move that to the left. So we're gonna play with the channel, which represents the horizontal axis, right and left. And that's it. So that's equivalent. So imagine that, we move that white markered line to this position. It's exactly the same. Okay. Now the first point is at 1.6 division.
Right. Yeah.
So then 1.6 division. The second point, maybe it's not clear. It's also clear. It's between this tick and this tick. So it's 2.9, but let's do it. Let's go. Yeah, 2.9 we can say. 2.9 divisions. Now we should multiply by the voltage per division for channel B, which is vertical, which is 1 millivolt. That's good, 1 millivolt. This will give you the voltage across the resistance R2, which is 0.01. Okay? So we still voltage now. To convert it to current, we should divide by this value, 0.01. So we're going to divide this by 0.01. Now I will change the share screen to my OneNote so you can see my calculations. You can see my calculations, right?
Yeah.
And it doesn't matter which is bigger, which is greater than the other, because so here I'm saying 4 minus, of course this is negative, but since I'm preserving the order, okay, also I subtracted the the small from the bigger series, so another negative, so they will cancel each other, so it doesn't matter. Okay, now we should divide this guy. Now this is representing VD or delta VD, we can say. And this guy representing delta ID. Okay, so it's like we have our curve in here. This is ID, this is VD, and we choose 2 points. Okay, this is delta V, D, and this is delta ID. Okay, so to know the resistance, the slope of that, we just need to divide delta VD by delta ID. So let's do that. This is 38 millivolts divided by this guy here, which is very big. So 0.01 will go up here, will be 100. Let's write it again. So this is 1.6 minus 2.9 is around how much is this? 0.9, right? No, it's not 0.4, it's 1 plus 3, right? 1.3, right or wrong? 1.3, 1.69, yes. 1.3 multiplied by, convert this is ohm, by the way. So this is 1 millivolt over ohms, 1.3. This will give us amperes, these two, and this guy will go up here, will be 100. So this will be 10 to the power minus 1. So 1.8 to the minus 3, 1.3 minus 1. So this will give us something to the power minus 2. What is this value? So it's 29, around 29, right? So it's 29. Yeah, 29.2. That's good. Okay, so equal to right? You got it? So it's similar to the 2.5 that we got before in the step-by-step or point-by-point experiment. Clear?
Yeah. Okay.
If it's not clear, just let me know. Don't be shy, huh?
So
Don't
only
be
the
shy.
change in why is that the only part that gets divided by the resistor?
Yes. And you know why, right?
Is it
Because
it's the current?
it is, yes, we wanted to change it from voltage to current. Okay.
So the change in X is already given to us in current?
The change in X is actually, so X here is voltage,
Oh, no,
right?
it's voltage. Yeah.
So we should keep it voltage. This is the voltage across the diode. Okay, this is ID should be the current across the diode. We can't measure it directly, so we put this resistance. We couldn't put it as 1 ohms, so we must change it to some very small value, 0.01, something very smaller than this value. Okay, but we take care of the change of this 1 ohm to 0.01 when we do the calculations by dividing by the value of the resistance.
Okay. And
And what?
and for experiment 2, that dividing doesn't really matter since it's just a 1 resistor.
What? What? I couldn't.
So, wait. So how does this equation change from experiment 2 to 3 since we're changing the wire?
So you will do exactly the same thing in experiment 2, but you will not add this, or you will not divide it by 0.01.
You just divide by 1?
Yes, you will divide by 1 since it will be, it's exactly the current. So you don't even need to divide by, because it's 1, If you divide anything by 1, it will be the same. So that's why if we have the chance to put it 1, we put it 1.
Okay, I understand.
Of course, in experiment 2, you will not get the same values.
Yeah, you get different ones.
Yes, because the output should be the same, something around 0.2 something. Okay, so you should get different values on the y-axis because we changed the resistance.
So this 0.92 value that we're getting, is that that's the resistance for the diode?
Yes. So this is the resistance. Look, it's a bit complicated. Okay, so we know that the resistance, by the way, has a formal definition. The resistance is the derivative of the voltages with respect to current. It's really, very big one. But in Ohm's law, since we use only resistors and capacitors, so it will just we just divide, right? But the actual definition is the derivative of the voltage with respect to current, which is the slope in Ohm's law, right? So in here, since the relation is not linear between the voltage and the current, if we do this relation delta V by delta I, or get the derivative, or using partial, like doing that dv by dvd by did, it will be a complicated equation. So what we are doing instead, which we know in our applications, that for example we're gonna play between 1 milliamps and 10 milliamps. Okay, so we're gonna look at the curve and we consider it as straight line between, we just pick some, this is the curve. We just pick, we know that we will work only between this value in current and this value in current. So we're gonna consider this portion of the curve as a straight line and calculate the slope of this straight line, and this will give you, an estimation for the resistance of the diode in that range. Okay? Clear?
Yeah, so for this lab, do you want us to put in snippets of our setup or just the graphs from the first experiment?
The graph from the first experiment, and for experiment 2, for example, or any other experiment, you just make a snapshot. Let me.
A snapshot of the
Yeah, you see my
the
screen
oscilloscope?
right now. You can see the other screen.
Yeah, so you want a snapshot of, say, this
That's
oscilloscope?
right. That's right.
Okay,
That's right.
okay. I think that's all that helps.
And of course, the calculations. Okay, so I
Yeah,
will look at the calculations and compare it to the what you have in here. So don't put, because you may put the same snapshot from experiment 2 and experiment 3. But I
okay.
will take care of that by looking at the calculations. They should reflect the measurement, the curve that I'm seeing in the snapshot.
Okay.
Okay.
Okay, thank you.
Any other question?
No, that was it.
That's it.
Yeah,
Okay. Have a nice day. See
you
you.
too.
Bye bye.